Hi everyone, my name is Mike Howells from Emerson and I'm coming to you today from our Skelmersdale office, which is the picture in the background there. And this is a manufacturing facility and I'm going to show you some of the products that we manufacture here a little later on. So the presentation that I'm giving today is to talk about solenoid operated valves, or SOVs. So that generally within the industry there's two types of solenoid valves. There's the direct acting solenoid valve, which is on the left hand side, and a pilot operated solenoid valve. These are sometimes called poppet valves or spool valves or pilot assisted valves, but they are generally two different types of operation. So the direct acting solenoid, as the name suggests, all the energy from the operation comes from the solenoid operator. They do tend to be higher power levels, but in modern times we've been able to reduce the power levels used on these type of products. The important thing is it operates from zero and in some cases even vacuum pressure, so there's no differential pressure that's required on a direct acting solenoid valve. There tends to be no bleed holes or bleed channels, which is what we need in a pilot operated to give the pilot air assistance. That's deemed to be less chance of malfunction because essentially you have two operations in a pilot operated valve. You have a direct acting operated valve on the end of the pilot operated valve to give that function. And this could be selected for standardisation, so if you're not too sure what pressures you're going to be using on plant, then this is the type of solenoid that you'll use. On the pilot operated version, we can have a lot lower power consumption. So typically on a direct acting we're looking at between 1 watt up to around 12 watts. On a pilot operated we can go down to a fraction of a watt, something like a 0.0007 watts, which is a piezo operator. It needs a minimum differential pressure to operate, so that tends to be around 2 bar, 1.5 to 2 bar typically. It has bleed holes and channels, and what that means is to get the air to the end of the solenoid valve, you need to have internal drillings to transfer the air from port 1 to the end of the solenoid. They tend to be more economical for higher flows because, again, in the direct acting you need a much bigger coil, and the coil is where you have a lot of the copper and the contents, which cost the money. And pressure is assisting the valve in operation. Now what we're going to look at is, when you look at the terminology in terms of a data sheet, what this actually means. So in valve basics, how you represent a valve is within ports and positions. So each box is represented, or each position is represented by a box. So typically 2 positions and 3 positions are common ones. 2 position is used on a 2-way valve and typically a 4-way or 5-way valve. So as we see here, each position is represented by the box. Typically it's 2 boxes. In some cases it can be 3 boxes, but that's in a 5-3 configuration. So now we've explained what the boxes are, or the positions, now we talk about the ports. Generally, again, when you look at a schematic or a data sheet, ports are represented by a number and a line to indicate the path. The rest position is shown with the port numbers, and rest is normally to the right, but not always. You need to check the data sheet and that will indicate to you which is the rest position. So as you mentioned here, you've got the port positions identified. A typical example of a 5-port valve is a 5-2. So on the right hand side there we have a 5-2, and then that will be the way the schematic is drawn on a data sheet or even on a schematic representation. So as you mentioned, typically we can have 5-2, but in some cases we do offer a 5-3, or there is a 5-3 available, and what that is a mid position. So typically to actuate that side, then you have some sort of actuation which is normally a solenoid, but it can be pilot or mechanical. And what happens is that box moves over to that side. So in the rest position, this is the configuration, and normally on this side you'll have a spring. But if it's a bistable valve, you'll have again a return which can be a solenoid or a mechanical. But typically this is the rest position, so if there's no electricity on this side, then it'll return to this position. And then what we have in some of the bistable or two-way type valves or dual acting is that we have two solenoids either side, and when either of these solenoids is not energised, so there's no power going to the solenoid, it remains in the mid position, so that's where you get a three-way valve. So typical ones is all ports blocked, which is an ABP. A configuration again in schematics is a W1. You also have pressure held, so that means in the mid position it holds pressure in the circuit. So that would be typically used on something like a cylinder, and the cylinder is needs to be held in that position, so it doesn't have to go to one way or the other, and it needs to be held. So you use that type of configuration. Or open to exhaust, again if we go back to the cylinder, in this configuration it will stay still. In this configuration it won't move, but the pressure will be held, so maybe if there's something on the one side which is weighted and you may have different pressures, it will be able to hold it in that position. And open to exhaust, what that means is if you have a cylinder and you need to move the cylinder, then you're able to do it with this, but when all ports blocked, it will block the cylinder. So that may be a cylinder or actuator which is used in the process industry. So some of the other typical products that we have are 2-2. So a 2-2 which is normally closed, not to be confused with electronics as a normally open. So in pneumatics we class normally closed as being closed. So if you look at a tap, a normally closed is a 2-2 valve. So you've got an inlet and an outlet. So when you look at a tap, that's a typical 2-2 valve. So in the normally closed position, the tap is closed. In a normally open, that would mean that the tap's always open. And then what we have is we have an exhaust port. So on a three-way, we have a port to go to exhaust. So in this position here, what you have is port 2 is going to exhaust. And at the moment, port 1 is blocked. And when you transfer it over, you transfer the port over, port 1 goes to port 2, so it will be flowing, and port 3 is blocked. That's a normally closed configuration. You also have a normally open configuration. Something that we used on solenoid valves is a manual override. Again, not to be confused with a manual reset, which is a different application altogether. But what a manual override does, it overrides the valve. So normally what you have is inside a 3-2 valve is a seat and a poppet. So the poppet is sitting on the seat at the moment, so the air is going nowhere. And what you do is, this is a cam, so when you turn the cam, it physically lifts that poppet off its seat and allows air pressure to go through. And you have different types, so this type with a circle is known as a screwdriver or a tool. So basically what you need is either a screwdriver or sometimes it could be a nut to be able to operate the manual override. And the important thing here is when you energise that manual override, if you walk away, then that manual override will stay in position. So these type of manual overrides where you have to physically go and remove the manual override, those are not to be used in the safety critical application, because obviously someone can come along, leave it in that position, forget it in that position, walk away, and it will be held in that open position. What can be used is an impulse type of manual override. And what an impulse is that you push the button, and then when you walk away, it goes back into the rest position. It's a spring-loaded button typically, and it returns back to a safe position. So within all solenoid valves, the way that we actuate a solenoid valve is through solenoids. So a solenoid is an electromagnetic field. And the way that it works, in the rest position, what we have here is we have a coil. And I'll show you a little video in a second on a coil. But inside a coil is literally hundreds or even thousands of copper wire which is wound round. And when you apply an electrical field, or when you apply a voltage to this, which can be typically a DC voltage, then what will happen is that will energise that coil and cause it to lift. Back in the old days in school, you may have done the nail trick where you wound copper wire around a nail and put a force on and moved it backwards and forwards. That works the same way. So we've got different sizes of coils. So again, I'll show you the manufacturing in a few moments of a coil. So this is a small coil for a smaller product, and then we have different sizes of coil going up to larger sizes. So again, I'll just show you that video of how a coil is manufactured.
This is the copper wire, the raw material of the core. And here we have the lady putting the bobbins onto the machine. This automated machine then connects the wire onto the two end pieces of the bobbin. And then, as you can see, the machine then rotates to put up to 100 or even 1,000 different windings of the coil onto the outside of the bobbin. Those are the components, and that's the end of the coil before moulding. That's the moulding material. And this is the moulding machine that we use to mould the coils. So this is a two-part machine. So the operator is now taking the scrap off and throwing that away. And because it's in two parts, sometimes the coils stick to the top half of the die. So we're carefully removing the coils from the top half of the die. And now we're taking them out of the machine. It's just cleaning off the process. And then for the next batch, the raw material has to be heated first. So this machine gently heats the epoxy before going into the injection moulding machine. And now we're going to put the cores that we've just produced inside the cavities. And we're going to inspect the cavities just to make sure that there's no foreign bodies and that the alignment of the internals of the core are correct. And then the machine is closed and we pressure injection mould the epoxy inside to complete the coil. As the coils are still warm, what we're able to do is to remove any flash from the outside, which we're carefully doing at the moment. And that's the scrap that comes from the centre of the core. Each one of our products is 100% tested. So this is the test machine. So we're carefully inserting the coils into the test machine. In this process, one of them is not aligned correctly, so it doesn't go through the test. So the operator has to realign the cores onto the diodes to make sure everything is connected. And then it goes through a sequence of tests to test the continuity, to test the voltage. And then when we've completed the tests, the machine automatically sprays the outside of the coils to make sure that the coils have passed the test. If they don't pass the test, then it will stop and not spray them.
Welcome back, and now looking at a 3-2 direct acting solenoid valve. What we have here is we have the air pressure going at the bottom here. It's currently blocked because the poppet is sitting on top of the seat. At the top there we have another poppet, another seat. So in the resting position the air pressure can't go anywhere, but the exhausting pressure can escape through the top of the core tube. When we energise the coil, that causes the core to lift. When the core lifts, that allows the air pressure from the port to go to the actuator, and at the same time it blocks the top port, and that allows the circuit to operate. And then when you release the signal, then it returns back. It normally has a spring inside to bring it back to its rest position. So again, a typical application for a 3-2 solenoid valve is on an actuator. And what we have here is an example of a spring return actuator. And again, this is a rack and pinion type. So rack and pinion, inside there what you have is you have a little worm gear. And the way that works is that when you turn it, you have pressure on the outside which pushes it together, and then when it opens you've got little gears inside there which turns the shaft on the bottom, and that operates a quarter turn valve. So again, in a second I'll show you an application where we're operating a cylinder which is the same way. But in this application what we have is, this is a 3-2 valve, but it's a universal valve. So what we're doing is we're coming in at port 3. It's in its rest position, so now the seat is sitting on top, so it's blocked. The exhaust pressure is going out to atmosphere. And what we're going to do now is we're going to energise that solenoid, so that solenoid is energised. We're coming through port 3 to port 2, which goes onto the outside, and inside there we have 2 pistons which open out. That causes a worm gear to quarter turn, and then that actuates something like a large valve, a process valve. And then when you return it, again, it reverses the process. So the poppet moves back onto its seat, the air pressure allows to go through, and again that completes the circuit. Now, within a lot of sort of management systems, what they have is they have what we call a configurator or a management code. So what we have is that a lot of manufacturing systems handle between 25 individual digits. Typically it's 15 to 25 digits is what an MRP or a manufacturing system can handle. A way of using that into greater numbers is to have alphanumerics. So each of these different digits can either be a number or a letter. So we can have up to 36 options for each one of these digits. So it may seem complex at first, but a lot of manufacturers use this type of system to identify their part numbers. And in a lot of cases there's a configuration chart where you can go to and you can identify the product from the part number just by breaking it up individually. So here we have an example of a configurator system. So this is a 2-2 valve. So again, you can see the configurations are normally open and normally closed, which we spoke about earlier. It's not pilot assisted because that configuration there means that it's a direct acting solenoid valve. There's no other parts to that. And then on this side it breaks it down of what the part number means. So each one of those digits represents a function, and then you're able to identify what the product is from the data sheet. Something that we use within ASCO is we use a valve selector system called Tom's Pave. So this is something that we use in general, but this can be implemented to any system. So each valve has to have a certain number of criteria to be able to specify the product, and a good starting point is this selector. So T means the type, O means the operation, M means media, S means size, P means pressure, A means ambient or what the working parameters or temperatures of the valve. V is voltage. Now this is a very common thing that we have when we have customers contact us, because in a lot of cases, yes, it can be 24 volts DC, but obviously we offer voltages all around the world, so we always need to know what voltage of the product is required. And E is enclosure. So when we're looking at T, T means type. So in this instance we've got a 3-way solenoid valve. So the type is, on this particular, you can have a 3-way or 2-way. So here we have a typical 2-way where we're going in through port 1 and out through the top. So this is a 2-way. So there's an example of a 2-way. So where you have 3 ports, but in this case we're blocking one of the ports off. So essentially it's a 2-way. This example here shows that we only have 2 ports. So we've got nothing on the top there. So basically it's in and out. And then we have 3-way. So again, this is a 3-way example of a valve. So in at port 1, the valve there as we mentioned previously, is in the rest position. So the energised size is clear, and it's just going out to atmosphere at the moment. So that's an example of the type. Operation, we can have universal, normally open, normally closed. So in this case, on the previous slide we had examples of normally open and normally closed. So this would be a typically normally closed valve. You can have an example of a normally open valve, and then you're going out to atmosphere, so normally open, normally closed. And then what you have here is a universal valve, and what a universal valve means is you can come in at any port. Not all valves are universal, you have to check on the data sheet. But what a universal valve can be a mixing valve, a distribution valve. You can have, obviously, as you mentioned, distribution, so in at port 1, diverted to 2 or 3, or a mixing valve where you have two medias coming together, and you can mix them by opening and closing them to give you that type of operation. So there we have a 3-way, 2 ports, so that explains the operation. And again, when you look at a data sheet, just be clear, because in a lot of cases you'd expect the normally closed position to come in at port 1, but if it's a universal valve it may come in at port 3, so always check the data sheet. And on the data sheet it will show you what the standard configuration of the ports are. Yeah. So in this example, you've got port 1 there, but this is a normally closed valve, so you could come in at port 2 for normally closed. On this one it can be a universal valve, so you can come in at port 2 if you want a normally closed, or in at port 3 if you want a normally open. And then you have a normally open valve which is straight through there. So always look at the configuration to see where the ports are, and then just make sure you're coming into the right port. So here we have some direct acting solenoid valves. So these are a series that are used within our portfolio. You have a coaxial valve there, we have a standard different types of 2-way valve. And these can be all different shapes and sizes. So I've got an example of a 2-2 valve, so again you can see there that goes straight through. Another example of a 2-2 valve in this beast, so again it's just a larger scale. And these are 3-2 valves. So as you mentioned previously, a 3-2 valve that's an example of a 3-2 valve. It can also be 2-2. If there's no port on the top, then it's a 2-2. If there's a port on the top, then it's a 3-2. And there's some examples of 3-2 valves. So again, if we go back to previously when we spoke about configuring a product, we've got an example here is I need a solenoid valve, 2-2, so we know that it's 2-way, 2 ports, 2-way, normally closed. We need it 24 volts DC. It needs to be G 1.5 inch for water with a manual override. Which of these products can you go for? So okay, let's break it down, and let's have a look at what the configuration is. So first of all, is it 1.5 inch? So these valves, as we can see here, are all 1.5 inch. What he needs though is a manual override. So all of these are manual overrides. You can see on the outside that it's indicated as a manual override, but he needs it in a fast lead time. So if he needs a fast lead time, these are the lead times typically on these 2 valves, so we can dispute those valves. MO means manual override, so when we look at this configuration here, this valve hasn't got MO, so that means that it's not manual override, but this valve has MO, which is manual override, and the configuration looks fine. So that would be the type of product you look for. So again, there's different types of 2-2 valves. So this is an example of a floating diaphragm valve. So what you have here is you have your main inlet pressure coming in here. You've got a small bleed hole, so what that does is allows the pressure to come through here, goes through on top of the diaphragm, and because the diaphragm pressure on the top of here is greater than it coming at the bottom, then that forces the diaphragm to come down and hold it shut. Okay, so this pressure goes up here, goes up, fills this cavity, can't go anymore, so what it does, it'll build up the pressure and push that diaphragm down. Because that diameter is greater than that diameter, it causes it to push. And then what we do is we energise the valve. So energising causes the core to come up, and then what it does, it allows that pressure then to relieve out into the second port. And then what you're doing is you're having a greater sort of resistance coming through the bottom there, that's going through and allowing a pressure to dissipate. And at the same time, when that pressure dissipates, then the overall pressure underneath becomes greater. That lifts the diaphragm up and allows the pressure to go through on the valve. Okay, there's another example of it working. So this is a hung diaphragm. So what hung diaphragm is it's not totally connected to the diaphragm. So in the previous example, floating diaphragm, there's no connection at all from the core to the diaphragm, it's just air pressure. With a hung diaphragm, it's actually attached to the core, so you've got two ways of that being connected. So you've got the core at the bottom. So it works in a similar way. So again, what you have is you have the air pressure coming over the top, pushing down. When you lift the core tube, the core is mechanically connected to the diaphragm, causes it to lift and allow the air pressure to go through. Okay, in some extreme cases, what you have is you have a condition called water hammer. So this is used in fluid. So typically, and you can get this at home, sometimes when you turn your taps off or the washing machine closes, you'll hear the pipes rattling, and what that is, that's a small case of water hammer. The way that you can alleviate a water hammer is having a small relief, and that small relief allows that flow rates to be able to absorb that high creation of water. So it just allows it to sort of soften the blow, if you like. So that allows the diaphragm to soften the blow and give you a better flow comparison. So floating diaphragm. So the way that this works, in a similar way, you have the pressure going through. So if we energise this, that allows the air pressure to go up the top. That relieves some of the pressure that's at the back of the piston. So that pressure that's at the back of the piston is dissipated. So again, you've got the spring force, but you've got this greater pressure going up against the spring. That allows that piston to push back, and then allows the system again to relieve. So if you just go back there, you've got the same configuration. So in the rest position, there's not enough air pressure to push that back, because what you have is you have a locked system at the back, so the air can't go anywhere, and the force at the back is greater than the force at the front. But when you're relieving that, that allows that pressure then to go through and out, and then at the same time the pressure at the back is relieved, and that pressure is greater, which allows the product to operate. So we've got another example of a hung diaphragm there, and that works in a similar way. So these are typically some of our products which we offer in different variations, and it depends on what the service or what the media going through the valve is, whether it's water, whether it's steam, whether it's air, whether it's special service, whether it's cryogenic. And these are typically some of the advantages and disadvantages of floating diaphragm, hung diaphragm, floating piston, hung piston. So within the process industry, the types of solenoid valves are an accessory on top of a package. So these are examples of packages. So what you have here is a large ball valve. That looks more to be controlled, as you can see, by a sophisticated system. So as well as a solenoid valve, you have a positioner, you have a switch box, you have all the configurations, and on the back of there is the actuator which controls the valve at the bottom. You've probably got a more simplified version of it here where you've just got an air filter regulator, a solenoid valve, butterfly valve at the bottom, and then on the end there you've got a much smaller package. This could be something like, I don't know, 60-inch valve. You could have 38-inch, 36 valve, and then on the end there's probably something like a 2-inch valve. So again, within our product portfolio, we're able to offer all the accessories, so everything that's on top of an actuator is classed as an accessory. So within Emerson, we're able to supply the full package or all the other parts, and again, obviously it's down to the specification or down to the customer's requirements. These can be different types of switch boxes or solenoid valves. So our direct acting solenoid or poppet valve, so this is an example of our product. So here we have a 3-2 valve, and as we mentioned previously, what you have is you have your inlet pressure there. It's sitting down on its poppet, so it can't move anywhere. When the valve is energised, it causes the poppet to lift, allows the air pressure to go through to the application, and then when the solenoid is de-energised, the spring takes over and allows it to go through. It's typically some specifications of a 3-2 direct acting solenoid valve. So this is our product, but again, a lot of products are very similar. They tend to be stainless steel. We offer stainless steel, aluminium and brass. The 3-2 on the actuated or the pilot valves tend to be between 1/2 inch and 1/4 inch. Minus 60 to 90 is a typical operating range. Can be up to 1.5 metre cube per hour, and you can have SIL rating certifications across the world, just depending on which product that you select. So as you mentioned before, if you remember previously from the 3-2 direct acting, again a typical application of what this is used, and what I'll do now is I'll give you an overview of a 3-2 valve in operation.
I have an example here of a 3-2 direct acting solenoid valve on a 1/4 turn spring return actuator. I've just reduced the pressure on the line just to replicate what happens with a low pressure circuit, and as you can see, the actuator is moving quite slowly each time I energise the coil. What I'm about to do is I'm about to increase the pressure on the actuator to around 6 bar, which is the working pressure of the actuator. And I'm going to perform the same test. And as you will see, this time the actuator will move a lot quicker based on the fact that the pressure is higher. There we go. You can see it's moving a lot quicker than it was previously. So that's an example of a 3-2 direct acting solenoid valve.
Now moving on to the pilot operated solenoid or the pilot assisted valve. So these can have many different forms. So we can have mechanical, what we can have is we can have pilot valves. These are just air to operate the ends, or we can have solenoid operated valves, and then there's different variations. So again, as you mentioned previously, what you have is you have a spool inside, and then on the end here is a 3-2 direct acting solenoid valve in its own right. But what you need to do is you need to get air from the centre there to this end channel. So inside there, there will be internal ports. In this case, there's the internal port which connects right to this channel here. So internally you have a connection from that port to this channel. That channel is blocked because at the moment it's in the rest position. When you energise the solenoid, it causes the core to lift. The core lifts, allows pressure to go against this piston. This piston moves forward, and as it moves forward it allows air pressure to go through different ports and different channels. And obviously you have a spring there, so when you de-energise it, the spring takes over. Typically the most important thing here is that this coil or this solenoid can be extremely low power. So this is an example of a piezo valve. So we use a 3-2 piezo valve on the end to energise the piston, and that can go down to 0.007 of a watt, so extremely low power. Again, what you have is when this piston moves forward, you need to remove the air in front of that piston, and typically there's two ways of doing that. Sometimes there'll be a slot or there'll be a breathing port in the front. Within our product, what we have is we have a non-breathing function. So what that means is that this exhausting air goes through into the exhaust channel. There's a connection into the exhaust channel, and that means it's just cleaner. So if you've got an aggressive environment which can suck in aggregates from the outside, or a dirty environment, as well as blowing out, it will also suck in, and eventually this cavity will be filled with whatever the outside environment is. So typically, just showing again a blow-up version of a 5-2 valve. And what we have here is a breakdown of the internals. So typically, as we mentioned, the spool moves across. Normally you'll have a spring to return it back to its rest position, or in a bistable valve it will be 2 solenoids and it will be a stay put. So if the solenoid is de-energised, it will just stay in the last position, known as stay put. So this is typically the actuating or the piloting side, and that's the return side. So as you mentioned previously, we've got 3-2, 5-2, we also have Nomura. Nomura is the interface that fits directly onto an actuator. And we have the availability to offer solenoid valves in different variations depending on the explosion proof or the atmosphere that you're working within. So on a Nomura valve you've typically got 3 types. So you have a safe area, which means that it's generally IP65 rating, so it doesn't have any explosion proof or any approvals. And then you have a valve suitable for zone 1 or zone 2, which is an EMB in this case we're going, but can be an EXD valve. And then you have an intrinsically safe. That type of product needs to be used with a barrier, and what that is the electricity that's used to power that coil is not enough to create a spark. So galvanic barriers or different types of barriers control that, so there's not enough electricity to create the spark.
So in this example I have a 5-2 solenoid valve which is electrically operated, and I've connected that to a 24 volt DC supply. What I'm now going to do is I'm going to energise that solenoid. The 5-2 solenoid valve is spring return, so when I remove the power to the solenoid it retracts the cylinder. So when I energise it, the cylinder comes out, and when I de-energise it, it goes back. What I'm going to do now is I'm going to replace the 5-2 electrically operated solenoid with a 5-2 mechanically operated solenoid. The 5-2 mechanically operated solenoid that I'm going to use also has an exhaust port regulator, and this is what is used to control the speed of a cylinder. So we're controlling the flow coming out of the cylinder. So now just in normal operation it moves backwards and forwards at the same speed. And now on the 1 stroke I'm going to be able to restrict the flow of the exhausting air. So now as you can see, that slows the cylinder right down. A cylinder's force is generated by how much pressure you put on the cylinder. So in this instance I'm going to reduce the pressure down, and I'm physically able to move the cylinder back to a return position. Now by increasing the pressure, I'm not going to be able to push that cylinder back because the pressure is too great. So I'm going to put the pressure up to about 6 bar. I'm not able to move it.
So some of the other examples of systems that are available are redundant control systems. So in this is a vaulting system, so you can have a 1 out of 2, a 2 out of 2, or a 2 out of 3. So 1 out of 2 means you have 2 solenoids, and if one of those solenoids fails, then the whole circuit fails. A 2 out of 2 means that if you have a 2 out of 2, then 2 of those solenoids need to fail, and that stops you having spurious trips. You know, if you have one of the coils that fails, the other coil still takes over, so you need to energise down both of those coils, which is classed as more reliable in terms of safety and reliability. So this is an example of some of the redundant control systems that we offer, and again, other people offer this type of system to be able to give you a more safe and reliable unit. As we're in Skelmersdale, I'll just give a quick overview of what manufacturing plant is that we have here today. So, as we mentioned previously, and I'll go in an overview, we manufacture the coils. We also manufacture cylinders. We can do bespoke assemblies. And this is typically something that's manufactured here. So this is a petrol vending valve. So as you can see here, these little red circular things, that's a different type of enclosure, but typically it's that 2-2 valve. So yeah, we manufacture petrol pump valves here, and we also manufacture urinal flush valves. So this is an example of a urinal flush valve, and you can see that we also use these on no-touch wash basins. So again, this type of application where you go and wash your hands, it's this valve, and this is manufactured here in Skelmersdale. And we also manufacture switch boxes. So this is an application of a damper valve. So this particular switch box can withstand up to 400 degrees Celsius within 3 hours, and that's used typically on a tunnel. So if you have an issue in a tunnel where there's a fire and you need to control that fire, they use that with these type of dampers. And what a damper does, it allows air to come in or it exhausts air out. And what you can do in a tunnel is, if you close the air, that will extinguish the fire by not allowing it to have oxygen. Or what you can do is, further down the tunnel, you can close all the vents this way, open the vents that way, and that will force the fire to go in a particular direction. But one of the constraints is it needs to be able to give a signal for up to 3 hours. So that's another one of the items that we manufacture here. And there's a few examples of packages or assemblies where switch boxes and valves and accessories are used. Thank you very much for your time. My name's Mike Hells. I've also got a YouTube channel, and some of the videos that we've shown previously are on this YouTube channel. Another aspect that everybody's talking about is sort of the IoT, or the Industry 4.0. So again, what that means is that within the solenoid valves is being able to have some digital feedback, and that digital feedback, you're able to use that as a sensor to see how long it took the valve to open, how long it took the valve to close, and then you can connect that to different devices. And we also have heart enabled products. Heart is a particular protocol which enables you to get more diagnostics, but this is something that everybody's working on at the moment and working towards. So there's my details. So if you need any help or assistance, then please get in contact with myself. And thank you very much for your time, and I'll speak to you again soon. Thank you. Bye bye.